Hello everyone, welcome to my channel. In this video, we are going to see about the common base configuration of an NPN transistor. So in common base configuration, the base terminal will be grounded and emitter and collector terminal will be biased with respect to the base terminal. Here we are going to discuss about the input characteristics and output characteristics of the common base configuration. When we go to the input characteristics, we have the input voltage VBE and input current IE. As we change the input voltage VBE, we can experience change in the input current. So let's go in a step by step way. First let's discuss the input characteristics and then about the output characteristics. So here if you can see, this is the graphical representation of a input characteristics of a common base configuration we are going to see now. So what happens? See here, this is VBE and this is VBC. Now since we are dealing with the input characteristics, we are going to see only this part. It is important to mark the direction of the current flow always. In NPN configuration, collector and base current goes into the transistor and emitter current goes out of the transistor. Here we are going to study the characteristics of VBE versus IE curve by keeping VCB as constant. That is usual we saw in the NPN transistor characteristics of a CE configuration. Here VBE is varied and IE is seen, change in IE is seen, emitter current is seen by keeping VCB as constant. So now let's have VCB as 1 volt. What happens? So as I already told, even in NPN transistor CE configuration, this junction, this PN junction behaves as a forward biased PN junction diode. So for VCB 1 volt, the voltage is increased and at cut-in voltage, we are able to see the increase in current. So even when VCB is increased or decreased, the cut-in voltage happens at 0.7 because it is a silicon diode. If it is a silicon diode, the cut-in voltage will be 0.7 voltage. In this material is made up of silicon. So now this is when VCB is equal to 1 volt. Now here we are going to increase the VCB, base collector voltage. That means increasing the reverse bias voltage and then see its influence on the emitter current. We are going to see whether the emitter current increases or decreases when we increase VCB and keep it as constant. Now let's have VCB as some 20 volt. So this is also reverse bias condition. This is also reverse bias condition. 1 volt and 20 volt. Now the amount of reverse bias is higher. As you can see, it is 20 volt. Now what happens? So during 20 volt, whenever a PN junction diode, this is also a PN junction diode, it is heavily reverse bias for 20 volt. Now the depletion region increases. It increases on both sides, but let's observe on this region, only the base region. So the effect of the increase of depletion width we are going to study. That effect is called as early effect. So what is early effect? If you can see this, only base region alone, the entire width is called as WB. The region right to that of P region, right to that of this center of the P layer is W. Left to that of this depletion width, depletion line is W effective. That is W effective. Now if you can see, the total width is WB of the base region. So WB is equal to W plus W effective. Now we have to see which parameter here you have to consider. WEFF is the parameter we have to consider. If you write the equation based on WEFF, let's see what happens. It is WB minus W. So what happens here? When W increases when this W increases. How does it increase? When the reverse bias potential is increased for up to 20 volt, this width starts to increase. If this width starts to increase, W effective starts to decrease. As the W effective starts to decrease further and further, what happens is the electrons which are in the emitter region are usually crossing the emitter region, and through the base region it goes to the collector region. Now here since the depletion width has increased so much, and only this W effective is the space allowed for electrons to stay here, the electrons won't stay here for much, and due to less width of this WEFF, more and more electrons come and accumulate and then cross over this region. So this increase in electron in this W effective region and crossing over of this region to collector region, electrons crossing from this region to base region to collector region, causes the emitter current to increase more and more. So this happened because the base collector voltage is 20 volt. For 20 volt, the emitter current is higher. Again, the concept working here is the early effect, where the W has increased. This is the W. This entire is the WB is the base region with base width modulation, we can call WB. This base width modulation is split up into two, W and W effective. W is the right portion and W effective is the left portion, left width. Here when I write the equation with respect to W effective, it is WB minus W. This W increases because we increase the reverse bias voltage from 1 to 20 volt. So this depletion width increases. So W effective is reduced, so that the electrons passing through this junction and reaching this junction cannot stay here for a long time, but more and more amount of electrons reach here. So due to this more and more electrons reaching this junction and crossing over this junction, this early effect is created, which increases the emitter current. So if you further increase VCB to 30 volt, still the emitter current increases because this effective width still more decreases. So this is the working principle of input characteristics. This is the characteristics curve and the underlying principle. Early effect is the underlying principle that makes this curve to appear like this. Emitter current increases when VCB, reverse bias, increases. Thank you.